Hi students, in this video we are going to start our discussion of electromagnetic induction. It is one of the most important chapter of class 12th and is very important for both JEE Main and Advanced. In this chapter we are going to see the points, we are going to see these topics: magnetic flux, Faraday law of electromagnetic induction, Lenz's law, motional EMF, induced field EMF, inductance, self-inductance, inductor, etc. LR circuits like the RC circuits and capacitors. Similarly, we have LR circuits and the concept of the mutual induction. Just like in the electrostatics we have done, in this chapter also, one by one topic we are going to take. So here we are going to start from the magnetic flux. So as already we know, we have the idea about the electric flux. Magnetic flux is also very much similar. Electric flux is defined as E dot ds. Magnetic flux is defined as B dot ds. Let us consider any magnetic field is there in the region like this. If you are seeing, pink lines are there, and this area vector is there. This one surface element is there, and area vector of this surface element is delta S vector. And the angle between the magnetic field and area vector is theta. Then the magnetic flux linked with this particular part will be defined as the dot product of magnetic field with the area vector B dot delta S. So we have B ds cos theta. Just like the electric flux, magnetic flux can be positive, negative, zero. It is a real scalar physical quantity. Its SI unit is Weber, or you can also say its unit is also Tesla meter square. Weber or Tesla meter square. Unit is going to be this. Now just like the electric flux means physically it is interpreting the number of field lines, electric field lines. Same way the magnetic flux is also physically interpreting the number of the magnetic field lines crossing the surface. Magnetic flux linked with a coil or circuit. Now in this particular chapter EMI, the varying flux is going to play a very important role. That's why this particular point has been written, that magnetic flux linked with a coil or circuit can be changed either by changing the B or area or theta. Flux linked with a small part or with a complete circuit is given by BA cos theta. So if you want to change the value of phi, magnetic flux, you can change it by either changing the B or by changing A or by theta or any combination of this. You can change B and A, you can change A and theta, you can change A, theta and B, all the things. By any combination of this you can change it. Now in this particular chapter, one very important thing is there, cutting of flux. Changing flux, cutting of flux means the same thing. Now you must know what is the meaning of the word cutting of flux also. Cutting of flux means when something is moving, some object is moving through a magnetic field, as the object is moving, is it cutting the field lines? If it is cutting the field lines means it is cutting the flux. And in that case, flux linked with the circuit is changing. So what I want to say here in short is, cutting of flux or varying flux, these two are the same things. Varying flux or changing flux or cutting of flux, both are similar, both are same, both mean same. This is an important point. It will help you in understanding this, right? Now I am taking some situation, 3 arrangement, in which I want to explain you that changing flux or cutting of flux means the same. In all the 3 cases, we are going to take one magnetic field which is into the board, into the screen, into the paper, and one pink color conductor has been shown like this. This is the conducting rod, and it is moving in the direction of the arrow. It is moving in the direction of this arrow, right? Now electric field lines are into the board and conductor is moving in the plane of the paper. Into the paper, the field lines are there and conductor is moving into the plane of the paper. So when it is moving here, if the conductor want to move, then it has to cut the field lines. So in this case, I can say cutting of field lines takes place. Now, another thing we'll see here is flux linked with the circuit is changing or not. In any time t, it sweep out some area, it sweep out some length. Say this particular length has been taken, this becomes the length. Now this length is, say, it becomes Vt if it is moving with V. Then it encloses some area. It encloses some area. Now, as it encloses some area, the flux linked with the circuit is BA. Area is in the plane and area vector is into the paper. So angle between area vector and magnetic field is 0. So it becomes BA. Now, as the conductor moves, area is changing. As the conductor is moving, this area is changing. This area, when it comes area, this area is changing. So as A is changing, it means the flux linked with the circuit is changing. So cutting and changing both means same, both takes place simultaneously. When there is any varying flux, then the flux is cutting also. It is proved here. Now take the another situation. Now magnetic field lines is into the plane, into the paper, and conductor is also moving into the paper. So area vector is going to be, here it has been shown, area vector becomes perpendicular to the magnetic field. So the flux linked will become BA cos 90. So it becomes 0. So flux is not varying, flux is constant and it is 0. Flux is 0. Now here you see is the cutting of flux is taking place. Now here the field lines are into the paper and the conductor is moving along the field lines, parallel to the field lines. So here no cutting of flux also. No cutting of flux. So no varying flux, no cutting of flux. Both takes place simultaneously. Another case you take here. Here one rod is there, field is into the paper and rod is moving in this way, means in this way. So if it is moving here, then you see the area swept is negligible. Here the area is tending to 0. And as the area is tending to 0, it means the flux linked with the circuit is changing. And here no cutting of flux also. So what I want to explain in short is varying flux and cutting of flux both goes simultaneously. In the coming topic, electromagnetic induction, we must be able to interpret that when the flux is linked with the circuit is changing. When the flux is cutting, only then we can say that EMF is going to be induced. In the coming part, we are going to see all these. So it is very important to understand that varying flux, cutting of flux, both means same. In some questions, it is easier to analyze in the way that flux has been cut. Then easily you can say some flux linked with the circuit is changing. In some question, they will give you the B as a function of time, then the flux linked with the circuit is changing. So for all those type of situation, this point is very, very important. Right? Now let's solve some questions. Take one question. say for example, we are having, don't take any arbitrary shape, we'll take circular only. One circular loop of radius r, this one, is kept in a uniform magnetic field, is kept in this uniform magnetic field B, and plane of the loop is in the magnetic field, then what is the flux linked with it? Now here if you see, area vector is, in this case, area vector is outward. Encircled dot means out of the plane of paper. Encircled cross means into the plane of paper. So area vector is outward and magnetic field is this way. So these two are perpendicular vectors. And the dot product of B into A into cos 90, then it will become 0. So the flux linked with this loop will become 0. Right? Another question you take. Consider one infinite long wire, say this, and another square loop type thing, say here. And in this infinite long wire, current I is flowing. And this distance is given as A. And this square loop is given as of side L. And we are asking what is the flux linked with this square loop. We have to find flux linked with, magnetic flux linked with square loop. Now, at different location of this loop, magnetic field is non-uniform. So we have to go for the integration. So let us say what we are doing at a distance x from here. I am considering a small width at a distance x here. This is small width dx. This small area element we are taking. So the magnetic field at the location of that element will be due to the wire mu naught I upon 2 pi x. And its direction is, from right hand palm rule number 2, we can say it is into the plane of paper. Means magnetic field is into this way. And then area of this element is L into dx. And area vector is also into the plane of the field. So what is the flux linked with this small element comes out to be B dot dA, that is mu naught I upon 2 pi x into L dx into cos 0, 1. So this is the flux. Flux is a scalar quantity, so we can integrate it directly. So into d phi. And the limit here, what is the variable? X is the variable. Mu naught I L upon 2 pi dx by x. Now x goes from where to where so that the limit will be taken. Loop is starting from here to here. So x goes from A, x is equal to A here, this is A, to here, that is A plus L. So you are going to integrate this expression between A to A plus L, and you are going to have the expression mu naught I L upon 2 pi ln A plus L upon A. This is the answer. This is the magnetic flux. Now this is 0. It is placed in uniform magnetic field. This one, first example, this is uniform magnetic field. This is the example, non-uniform magnetic field. Take another one. One more question you take. If we have a loop placed in uniform magnetic field, say, not better we take the square loop, or we'll do one thing. You consider it is spherical surface. Spherical surface. Means spherical surface, three-dimensional space. And here the magnetic field is present in this direction. Uniform magnetic field is present. Right? Uniform magnetic field is present in this direction. Now, what is the magnetic flux linked with this sphere? Question is magnetic flux linked with the sphere. Now, here in this question, you have to use the fact that physically flux is interpreted as the number of field lines linked with the surface. So here if you see, the number of field lines entering and number of field lines leaving are equal. So the magnetic flux linked with the sphere will become 0. Right? So magnetic flux linked with the sphere becomes 0. Take one more example. Let us consider a cube. This type of thing you assume. Like this. Now here let us say it is placed in a magnetic field. Say this is the origin, this is the x-axis, this is the y-axis, and this is the z-axis. Here it is placed in a magnetic field which is given by B naught x I cap. B equal to B naught x I cap. And along the y and z axis it is 0. And we have to find the magnetic flux linked with it. Now if you see here, see it clearly, magnetic field is only in this direction. Now there are 6 faces. The top face here, marking you see I am saying this is the top face. And this is the bottom face. Now for this top and bottom face, area vector is along the positive y-axis and along minus y-axis. But magnetic field is in this direction. These two are perpendicular. These two are perpendicular. So the magnetic flux linked with this top surface and this bottom surface will become 0. So first thing I'll write, magnetic flux linked with the top surface equal to flux linked with the bottom surface equal to 0. Top means parallel to the xz plane. Bottom means parallel to the xz plane. Now you see this plane, front plane, this one, this face, front plane, and this backward one. Now area vector for these two is parallel to the z-axis, but magnetic field is along the x-axis. Magnetic field is along the x-axis. So the flux linked with front and back will be also 0. Now left two surfaces only. Now left one is this surface and one is this surface. One is this surface, other is this one. Now the magnetic flux linked here. Here the area vector is along the x-axis and magnetic field is also along the x-axis. So here let us consider this cube of side L. This I forgot to tell. Consider a cube of side L. Now it is given B is B naught x. So what is the value of x here? L. So what is the value of the magnetic field for the surface ABCD? For this surface ABCD. So flux linked with ABCD is equal to B naught. B naught is, sorry, B. B is B naught into L. and area vector is L square, right? So this is the flux linked with ABCD. And if you see the other face parallel to it, this one which I am marking it, this surface, then the flux linked with this surface is 0. Why? Because here the field is 0, because magnetic field is B naught X, and for this location X is 0. So I am marking it here by another name, say UVWX. So flux linked with UVWX is equal to 0. So if you see, the flux linked with 5 faces is 0 and only with ABCD is non-zero. So the total flux will become equal to B naught L cube. This is the magnetic flux linked with it, right? So if you see one more thing, you see, to identify only whether the flux linked with the circuit is changing or not, cutting, etc. Example 5 you take. Let us consider some magnetic field lines is there into the plane of paper like this. Encircled cross we represent by into the, and I am not keeping the circles of across all the crosses. And say for example, one this not rectangular, rather you will say this type of arrangement I am taking. This type of semicircular rod. Here, this is also present, this is also present, this is also present. So when this is moving, when this rod is moving this side, then is the cutting of flux is there. Now you see, let us consider this as A, B, C, and this you write ADC. This is a loop. Now as ABC moves, means as the loop is moving, ABC, arc ABC, circular arc, semicircular arc, it cuts the field lines. It cuts the field lines. Field lines are entering. Field lines are entering. As ADC moves, it also cuts the field lines. Right? Now from here field lines going here, or if we consider total ABCDA, if we consider the total loop ABCDA, then whatever number of field lines are entering from here, same number of field lines are leaving from here. So the net flux linked with the loop ABCDA 0. Flux linked with ABC and ADC are equal in magnitude, but the total, one is positive, one is negative, one goes in, one goes out, right? So this is all about the magnetic flux. Next part we'll see in the next video.